So we're going to get right into it, talk a little bit about the future of JRuby. We've got a little short intro of what it is, but like Tom said, we got a lot of slides, so we're going to get right into it. So first of all, basically, what is JRuby? How many people here have used JRuby for something? Awesome. How many people have something in production right now with JRuby? All right. So like 3/4 and about a half of the room. That's cool. We expected that folks coming to this would probably be more on the JRuby side of things. So JRuby, of course, is Ruby on the JVM. And this means a lot of things to a lot of people. A lot of them aren't good things, unfortunately. You get stuff like this, and you know, people, it's all about applets, and the JVM sucks, and people actually go to our code base and look for stuff like that. But I mean, the bottom line we always try to get across is really that JRuby is just Ruby. It's a Ruby implementation. It happens to be written partially in Java, happens to run in the JVM, but it's just a Ruby implementation. So basics about JRuby before we get into talking about futures, where we're going with it. It right now is compatible with Ruby 1.8.7 and 1.9.3. This is going to change in the future, as we'll talk about. Mostly written in Java, more and more code being written in Ruby, but even the Java code we have is pretty clean. We've got us pretty standard coding conventions that we like our committers and contributors to follow. And the coolest part about JRuby, and the reason that most people come to JRuby, is because the entire world of the JVM is available to you. The GCs that we've got available, all the different platforms, the JIT, runtime, and then of course all of the libraries and languages that are on the JVM. So it's a Ruby on top of this platform that brings a lot more than just Ruby to the table.
Okay, I'm going to talk a little bit about JRuby, how we version and branch, and how we've evolved our development a little bit. When we do a significant release of JRuby, we do all of our development on master. Once we hit that 1.6.0, as you know, any project that hits 1.6.0 isn't like quite ready to be used yet. So we usually do one or more point release until we feel confident, and then we create a maintenance branch. In the case of 1.6, we did it after 1.6.1. JRuby 1.6 was going to be the great 1.9 release for JRuby, and it wasn't. Most of the 1.9 stuff was there, except for encoding, which
turned out to be kind of important.
A tremendous amount of work. And so time marches on. A year later, we put out a preview release on 1.7. We're plugging away on master, working on the next great thing. Oh, another 5 months, 1.7.0 comes out. So for a year and a half, we're on this dual branch development mode. And what ended up happening is we had so much fun on master that not a lot of stuff made it to 1.6. And the branches kept getting further apart, and we did merge stuff when people asked for it, but this was not something that we wanted to repeat.
Right. We really like to keep our releases short and closer together, and keep fixes going to the right places, to the releases people are using.
So when we started working on 1.7, you'll see that we didn't actually create a maintenance branch until after 1.7.5. This was us
trying to keep it real.
Yeah, I mean, it's discipline and pain. I was trying to think of the right word to represent the word pain.
Rather than going off on a completely new version of JRuby, we forced ourselves to do a lot of incremental releases of 1.7 and keep improving it.
And we knew that we were going to be working on a major release, so we wanted to make sure that things were really solid by the time we started doing that. And in fact, we almost did this at 1.7.3, then realized that we were still missing encoding work on zlib. Encoding's really hard. So the other things that we're going to do to try to make this dual branch development work better is we're going to make sure that we put out a release at least every 3 weeks. This is to keep us honest. If we go and put out a release in 3 weeks and it only has one fix in it, then we're not really doing our jobs. So this will keep us honest. And the other big change is that anything that involves compatibility, we're going to apply to 1.7 first. And we're constantly merging back to master. Things will be golden. I think we've finally found our sweet spot here. So let's talk about the next major release. One big change, Charlie will show some stats in a little bit, but we're only going to support Ruby 2.1. It's coming out sometime next year. It should line up good with MRI. This is going to be awesome. Supporting multiple modes of Ruby at the same time is really painful. We're probably going to be Java 7 and higher. If there's any people that use Java 6 and you're not going to be able to migrate by next year, just talk to us. We want to hear who those people are and what your stories are. We want to be modular, both at a packaging level, because platforms like Android, they want to have as small a jar as possible, and also at the source level, because things like Google App Engine, they don't support sockets, so they shouldn't have to compile against that. Look at this picture, and now look at this next slide. We're going to be breaking lots of APIs. This is the first time that we've actually decided to break a lot of APIs. It's been 10 years, or maybe more than 10 years, so we're going to just clean up all the crap that we've hated for 10 years, and we're going to have a lot of fun doing it.
This mostly affects like JRuby Java-based extensions. Obviously, the Ruby compatibility won't hurt at all, but libraries that are written in Java for JRuby may have to make some changes.
And we have a plan for reducing the pain with regards to embedding, and I'll talk about that a little bit later. And we also have a brand new runtime, which we'll talk about later. So I haven't said what the major version number is yet. The natural one would have been 1.8, but JRuby 1.8, which supports Ruby 2.1, would have been kind of weird. 1.9, 2.0, same thing. 2.1, that one actually does kind of make sense because we will support 2.1, but then we would release a 2.2 before MRI did, and then that would be weird. So we should have did this for our version number. We should have went from 1.7 to 8 like Java, but we're weird like that. Well, we'll see. We could have picked X and went to 10 like Apple. We kept joking, we'll just call it 9,000. I hope people can hear this.
Vegeta, what does the scouter say about his power level? It's over 9,000! What, 9,000? There's no way that can be right.
Okay, and if you couldn't hear that, he said it's over 9,000. But our next version is actually JRuby 9000. And for those people who don't like it, it's just a number. Get over it.
Now, the work on JRuby 9000 has actually already started. It's been going faster than we expected. This is just some simple stats comparing the JRuby 1.7 line with master. And we're stripping out a ton of code by removing 1.8 support, not having 2 or 3 copies of the standard library, getting the whole of JRuby much smaller. Probably the best one here is the complete jar, which is JRuby plus the entire standard library all in one file, is already down by about 4 meg. So we're getting better and better at shrinking down the runtime. I'll talk a little bit about what we're doing to improve the ecosystem going forward. Probably the most difficult part of developing JRuby, and where we've definitely spent the most amount of time, is simply on compatibility. We're constantly chasing a moving target, MRI, which has at various times had very fast development progress, added large features. And so we've always kind of been trying to catch up. What we're hoping is that with JRuby 9000, we'll be able to match directly up with the 2.1 compatibility. Hopefully right around when they do 2.1 release of MRI, we'll have all the features implemented. And then we'll be at our leisure to release or continue working on performance runtime stuff. But hopefully now being able to stay in lockstep with MRI and the features that they add. So things that we know are still missing. From 1.9, spawn plus all of the different file opening options and redirects and other things, there's a lot of those pieces missing. Largely missing because the JVM zone process management APIs don't support most of them. It's very difficult to do them. We'll probably have to do a native call out to do these have full support for them. We do have full transcoding support now, and it does work well. We fixed a ton of issues and did a complete rewrite of I/O, transcoding, and coding stuff for 1.7.5. That seems to be doing well. We haven't gotten any real major issues with it. But we're using all the JVM's character-based UTF-16 transcoders. So everything has to go to UTF-16 and then back out to the target encoding. That's overhead we'd like to eliminate by porting over the same byte array-based transcoding support that MRI has. And that's probably going to come up soon. 2.1 stuff that we know we're missing. Prepend, we don't have in there yet. Shouldn't be too difficult. Refinements are going to be officially a feature in 2.1. I worked pretty closely with a lot of the MRI folks to try and strip down the feature a little bit, make it not as invasive, not as damaging to performance. And I think we're confident now that we can implement it in JRuby without a major impact. But it's not there yet. We'll have that hopefully by the time MRI 2.1 comes out. And then there's enumerator enhancements that are not quite there yet. Size is there, lazy stuff. Size isn't there, lazy is. Little bits and pieces from 2.1 that we still need to implement. We're always trying to work on improving the platform in general, not just for JRuby either. For example, lots of gems for thread safety I'll talk about later. Gems like FFI for calling out to native libraries, database access, image stuff, all these things to fill in the blanks for JRuby users. We're constantly working with gem authors to improve performance of their libraries on JRuby, improve performance in general in a lot of cases, fix threading problems. More and more Ruby gem authors and library authors have started to pay attention to threading, testing stuff on JRuby, testing in concurrent situations. So we're looking pretty good in that area too. Probably the biggest thing is trying to get more Rubyists testing their stuff on JRuby. Travis is a nice, easy way to do it. Otherwise, an RVM setup, getting something local that you can test on to help improve the whole platform. We're also going to continue trying to improve how closely we work with MRI. I've been active on a lot of issues. All of the JRuby team members have been active on issues in the Ruby bug tracker, especially feature-related features for Ruby that are going to affect JRuby. Trying to do more on that, especially since JRuby is kind of leading the way on concurrency and parallel execution of Ruby code, trying to push that forward and take the lead on figuring out how that's supposed to look. I'm actually a committer on MRI, and I've fixed a few things. Hopefully doing more of that in the future to try and clean up standard library, get some threading utilities in there, get some cleanup done. And just in general, trying to help improve the process of evolving Ruby based on how we do JRuby development. So let's talk a little bit about performance that we're going to work on in the future. So there's a lot that we can do to continue making JRuby faster, make Ruby in general faster. The challenges are we've got lots and lots of dynamic calls, very dynamic object structures, lots of indirection around. The structure of the objects isn't even fixed at startup time. It's defined as instance variables appear. So there's more and more we need to do. The first step of what we do as far as performance is basically just compiling things down to bytecode. The JVM likes bytecode, obviously, and that's what it optimizes. So that's the simple first step. What we can do more of here is generating real classes for the Ruby classes that you create, so the JVM sees a normal Java class object, generating instance variable tables that are directly in the object rather than as a tag-along data structure, shrinking everything down, reducing the amount of indirection that we have. We've also been hitting Invokedynamic pretty hard. Invokedynamic is a feature added to Java 7 that basically makes it possible for dynamic languages to plug directly into the JVM and optimize like any statically typed language. It has a bytecode, of course, that represents a dynamic call, and then a series of handles and manipulators and argument modifiers to basically describe how to do the dynamic call in a way the JVM can optimize straight through. Now, does this actually work? Does it actually optimize well? Well, this is one of the benchmarks I've been showing. It's the red-black tree C extension and the Java extension compared to the pure Ruby version. So if we look at Ruby 1.9 and 2.0 with the pure Ruby version, Ruby 2 does a ton of stuff to improve performance. Some of these are inspired by what we've done in JRuby, reducing call overhead and so on. But there's definitely a good improvement in 2.0 and 2.1 as far as straight-line performance of Ruby code. Maglev and MacRuby, I don't know if anybody's using those lately, they do better. They have actual JIT optimizations that they do, and then are able to be about twice as fast as Ruby 2.0 just by doing some fairly simple JITting. Rubinius has more of an optimizing JIT, and so running Ruby code, it actually starts to get comparable to the C Ruby versions running with the C extension. The overhead of the Ruby code that wraps the C extension and the callouts to the C extension start to become more overhead for MRI here. And now these are the cool ones, actually. So this is JRuby on Invokedynamic on Java 7 or 8 with the pure Ruby version in the gray here. And it's actually not quite twice as fast as Ruby 2.0 with the C extension. So we're actually able to run the Ruby version of the red-black tree extension, or red-black tree library, almost as fast, well, faster in some cases, as the C extension. And then, of course, JRuby and the Java extension, since it all just looks like Java, regardless of whether you're calling into a Java library or calling from Ruby code, the JVM is able to do a significant optimization on that. Now, this is great, and Invokedynamic definitely works as far as the performance you can get out of it, but there's a caveat here. So Invokedynamic, when it first came out in Java 7, was very slow. It got fast in the second update to Java 7, but that was also broken. There were some severe issues that when you deploy it in production, it wouldn't run properly. 7 update 40 rewrote it, and it is now 100% compatible, 100% safe, no bugs with it, but it's very slow to warm up, and it uses significantly more memory than the original implementation did. So it's probably going to settle more on Java 8. We have had few users using Java 8 with Invokedynamic, not reporting any of the issues that we had during the Java 7 timeframe. So if you're interested in getting the best performance out of it, the Java 8 preview builds be a good way to test it out. Now, because of all these issues, we've continued to look at other options. One of them that came up recently is a couple non-JVM JIT projects out of Oracle. There's one called Graal, which is basically an API directly to the JIT in the JVM, and Truffle, which allows you to take language's AST, abstract syntax tree, and basically convert it directly into Graal calls and optimize it down. Now, the early numbers on this have looked good. Oracle did spend about 6 months doing a proof of concept Ruby implementation on top of Truffle. That's about 5 or 6 times faster than JRuby. But the problem here is that they've only got about half of, in this case, Ruby spec passing. And there's a lot more that needs to be done. There's probably 2 or 3 years worth of work to get that going. What we're hoping is that maybe we'll have some time to explore building a Truffle or Graal-based backend in JRuby itself.
And once you add some of the extra vagaries of what Ruby does, that performance is probably going to drop.
Yeah, exactly. There's a lot of other stuff that they have to put in there. And these libraries are a big part of the performance, too. So, I'll hand it over here to talk a little bit more about the new IR-based compiler that we're also working on.
Yeah, so IR stands for Internal Representation, which is probably not the most inventive name that we could have come up with, but it's our new runtime. Subramana Sastry created the bulk of IR up to this point. He's a guy who's got a PhD in writing a Java optimizing compiler. And he basically created an architecture that's very similar to a compiler architecture if you read like the Dragon book or took a course at university. And we really wanted to create a new runtime because we were fed up with trying to do these optimizations directly from the AST. We also wanted something that we weren't going to want to rewrite in 5 years from now. So we wanted it to be easy to go and plug in new optimizations and have a lot of growth. So here's what IR sort of looks like. At the top, for JRuby 1.7 and below, we'll lex and parse Ruby code and generate an abstract syntax tree, and then we'll either interpret that until it gets warm, and then we'll translate it to Java bytecode as part of a JIT. But in the new IR landscape for 9K, we'll perform some semantic analysis and translate that syntax tree into a set of instructions and operands that represent Ruby semantics instead of just syntax. We'll create some supplementary data structures like a control flow graph. After that, we can run a series of optimizations on that, create some more data structures, change some of these existing ones, and then hopefully we'll be able to maintain a very thin layer for an interpreter, pretty simple bytecode generation layer, and we'll be able to expand that out later on to things like Dalvik.
Ideally, trying to do as many optimizations as possible before we even get to the point of generating bytecode for it.
So here's our first look at what the instructions are. I'll just go down a few of these. At the very top, we make sure that there's 2 required arguments with check arity. The next 3 instructions, we assign the parameters A, B, but then we also assign the closure in case someone actually supplied a block to it. Down at line 6, you can see C equals 1 looks like the left side. And lines 8 and 9, represent D equals A plus C. This one doesn't quite read as nice, but it's still pretty simple. We can do all the optimizations that you would expect if you took a compiler's course. If we find code that we can remove that won't affect how the program runs, we can just eliminate it. If we see a constant value that we know doesn't change, we can just propagate that to where it's used and get rid of the dereferencing from the variable. We can inline methods and blocks, though we're not actually using that a lot yet.
We do have some early inlining support, though, so it is possible.
Oh,
we have managed to make it work.
It totally works. It's just figuring out when to do it is a much harder problem than we realized. So here, if we run a couple passes, you can see that we got rid of about half the lines of code. You can see we didn't use closure, so we just eliminated that. Same with the variable b. On line 6, c equals 1, we know that c never changes, so we propagate the value 1 down to the plus call, so now we're doing a plus 1 instead of a plus c. And in general, we're reducing overhead. We have things like block.isGiven littered through our code base. This is a check that's really fast, but it's not free. If you compare that to the dead code elimination aspect of receiving this block as an instruction, if we can eliminate it, then we're doing absolutely no work. And no work's better than some work.
Right. And then as we're able to do some more inlining, a lot of these same optimizations will propagate through multiple methods. Like if it turned out that a plus 1, a was also a fixed num, well, maybe we inline it and it actually just turns into 2 at that point. So there's a lot of stuff that we can do to optimize through code once we get the inlining working.
And you can just keep reapplying some of the same optimizations after that inlining. It just keeps boiling down.
That's the black magic of compiler optimization. When do you stop? All right, so concurrency-wise, most folks know that this is the situation in general. Ruby 1.8 was green-threaded. Ruby 1.9 plus all have actual native threads, but don't allow parallel execution because of the global lock. Whereas on JRuby, because it's on the JVMs had real parallel threads for a long time. We do actually have real threads. You can actually saturate an entire machine with just one JRuby process. And where this really comes into play is the cost of deploying wide applications for a lot of users. If you look at a 10-way concurrent application in MRI, each process is maybe 100, 200 megabytes. If it's 200 megabytes, that's 2 gigabytes of memory that you need to allocate. And that's not a trivial instance. It's not a huge one. But then we need to scale this thing up. And what if we need to handle 100 concurrent users? Well, then we need to have 100-way concurrency in MRI, which means 100 processes. Now we're getting into 20 gig. This is getting into the very high, very expensive end of, for example, EC2 instances. We recently had someone make a migration to JRuby and saved something like $15,000 a month by moving from a whole set of extra larges down to like 5 mediums. And so there are real tangible benefits to making a move to JRuby and getting threading working well for your application. Look at how it is in JRuby. One instance, it's going to be a little bit larger as a base cost, but you can handle 10 instances, 10 concurrent. You can handle 100 concurrent. You can handle whatever the machine's capable of handling pretty much with one process. Maybe you have one for fallback, but it's a tremendous difference as far as scaling. But there's challenges here too, and this is where a lot of the future work needs to come in. The Ruby world and the Ruby libraries out there are still kind of growing into concurrency, growing into parallelism. There hasn't been a big emphasis on threading or concurrent execution in the Ruby world. And so there's more that we need to do. We need tools to make it easier. We need to help make these libraries thread safe. These are some of the key unsafe operations that you're going to see in libraries that aren't thread safe. Concurrent read and write on data structures like array, hash, those are not guaranteed to be thread safe. So if you're not doing mutexing around those, they can be a problem. A lot of people don't realize that calls like this are not done atomically in any implementation. There's a possibility of a thread jumping in there and doing the same increment at the same time. You get different results out of it. In this one, if my cache really, really needs to be allocated only once, this is not a safe way to do it because it's very possible that you may allocate 2 of them if 2 threads get to that code at the same time. Thread pooling's tough. We need better libraries to do that. Ideally, some things that start to get into Ruby core. And then just coordinating between threads, better ways of communicating and synchronizing threads together. So a few gems that we like, some of these we maintain, some are from friends of ours. The thread-safe gem provides a concurrency-safe hash and array. It also provides, I'm not showing here, a cache class, which is it's hash-like, but it uses some of the techniques that the Java concurrency engineers use for concurrent hash map to do fast multi-threaded hash map implementation. But otherwise, it's pretty simple. You construct it, you use it like a normal hash almost, and it works pretty much the same way. Hamster is a set of persistent collections for Ruby. Now the difference with persistent collections is that you never mutate it in place. Every mutation operation gives you a new reference, which is that old collection with this change applied to it. So the object you have in hand is always basically read-only, and you know that no other mutations happening in the system will impact your reads of it. So it's 100% safe as far as concurrency goes, and the nice thing about it is avoid any sort of locking or magic tricks under the cover. You're just getting a new view of this data structure that everyone else still has their old view of. I won't walk through the whole example here, but it's fairly simple to use. Every mutation, you just assign the result, and then you've got your new collection as a result of it. So for those atomic updates, or equals, plus equals, and so on, there's the atomic gem. Atomic gem basically gives you a wrapped value that you can do atomic updates to, increment it atomically, perform some Ruby action atomically, and it will only happen if nobody else jumps in. So you'll get the atomic right. Other threads will have to retry again, but it guarantees that no one's going to step on each other. This is a simple example. We create an atomic object at the top with just a fixed num0. We can get the value out. We can swap it for another value. And then the more interesting ones doing compare and swap. If the existing value is 2, put 3 in there. And then the second line, since we know it's not 2 anymore, that's not going to happen. This is how we keep threads from stepping on each other's updates. You can try to make an update only if it's the same state you expect. Down here, doing more advanced atomic updates, update with a block will only make that change if no other thread jumps in there at the same time. And if another thread jumps in, it'll try and make the change. In this case, it'll redo that block, and down here it'll raise an error. You can decide whether you want to try and continue doing this update. So the bottom line for these libraries is that concurrency really can work in Ruby, and there's a lot of people doing highly concurrent applications on JRuby right now, but we need the right kind of tools and the right patterns to do it. Immutability really helps. Having some of these sort of data structures helps. And testing on JRuby is really the only way to know if your library is going to be thread safe. We've got the most extensive threading support, and we've had it for the longest, so it's just best if you test on JRuby to make sure.
Okay, I mentioned earlier that I wanted to talk about improving embedding, especially since we're moving to a new major version that's going to break APIs. First thing is public is similar to public in Ruby in that once something's marked public, anything can call it. We have a huge code base, and we need to mark a bunch of things public. Unfortunately, because it's public, then any native extension can call it as well. And I don't blame people for doing it. They're calling these methods because they have to, and they probably represent gaps in our embedding API. But we need to actually signal our intent that we think that these are blessed APIs you can use versus we don't want you to use these. So we're going to also provide a tool, and let's look at the solution, or part of the solution.
This is actually a problem that MRI is faced with the C extension API. Without hiding some of it, everything becomes the public API, and that's a big reason why C extensions are hard or impossible to support in other implementations.
Well, C doesn't have visibility at all, so we get a little bit more protection, but not a lot. So I'm not going to teach people how to go and write annotations in Java. This is RubyConf, but this is really great. I'm just going to talk about annotations a little bit. This is metadata that you can attach to first-class concepts in the language. So in this case, we're creating an annotation called extension that we can attach to methods. So we'll just put add extension in front of our method declaration. And and then we specify that it has a runtime binding, which means in your live running Java program, you could actually ask that method at runtime, are you an extension method? So this metadata concept is really cool. In usage, in our source, we'll just mark the methods that we have as extensions. And then and our native extensions. We can use those and then run a tool. We haven't actually wrote the tool, but it'll be integrated into JRuby lint. It'll examine your jar, and it'll give you a report of things that you are using that aren't blessed.
Right. This is part of the transition. We know we're going to break some of those external APIs, but we know the ones we're going to bless as official and can give reports to any library that's out there using the bad APIs, what they're using now and what they need to change to.
We kind of get a double benefit as well because we can actually write a documentation generator and we can actually generate an embedding document from these annotations. And the reason why I spent a little extra time on this was because wouldn't it be really great if in Ruby 3 we actually added a metadata facility so that we could go and attach stuff to methods? There's just so many uses for this. It'd be really nice to consider adding something similar to Java annotations. We're going to go and cover some projects associated with Google Summer of Code. JRuby actually had its own organization for this, and well, examples are probably the best way to show.
We have some Google Summer of Code people here. There's one in front. Okay. I think maybe the other ones might be. There's one other that's here, I think. I haven't seen them around yet, but we had 10 people this year. How many did we have last year?
Oh, it was more.
It was more. I think
it was
we had
like
13,
14 or
we
something.
had 13 students last year, 10 students this year. So we're really trying to help get more students into JRuby and into Ruby in general.
The first one is actually from last year, but it kind of fits into the talk about IR. We realized we had a problem with IR, and we sort of still have that problem. This diagram totally shows it. We're doing more work. If you think about JRuby, the one thing that we're known for that we don't want to be known for is our startup time. So our startup time's
Add a little more overhead to that?
Yeah, let's add more overhead. But we realized this before 2012, and we had Alexei work on a persistence project, basically similar to just a compiler. You just save your persistent data, and then you read it in instead of having to recompile. So if the file's up to date and it's been saved, you just read that and save having to compile. And ultimately, we have a break-even point. We have to be able to read that off a disk faster than we can actually compile. And this is kind of a lie. We actually have to be faster than 1.7 today, or people are going to go, why did you slow JRuby down even more for startup? Unfortunately for this project, it ended up taking longer to read the data in than it took to actually compile it. But it basically boiled down to we were saving way too much data. Size really does matter for read speed. Also, we realized that a majority of the stuff that we were actually reading in, we never actually used. So we want to be more lazy. I'm not going to talk about interning. I was, but we'll cut down. So we're going to use a binary format. And the most important part is that we're going to do incrementally loading to be lazy, and this diagram will show you why. If you look at all the basic operations you would do on a day-to-day basis, you'll notice this really strange ratio. It's an 80-20 ratio. 80% of the code that you actually load when you start up each of these activities is never actually called. Now, maybe for a longer running application, it does get called, but it seems like for startup and common activities, the 80-20 rule applies, which is really, really weird.
Yeah, it's weird that ratio applied almost across the board.
So if we define the methods, but we don't actually parse any of the bodies, then we're obviously going to be doing a lot less parsing. Our sense was updated. Eric West is here. Let's stand up quick. You have to embarrass him a little bit. If you haven't seen our sense, it's a library that you can go and install and put into your editors like VI or Emacs, and it can do simple things like code completion, but it actually makes smart choices because it actually is a full type inference engine. In this case, this is a pretty simple form of type inference, but it can figure out a surprising amount of stuff. So it's something worth looking into. But before I talk about how to do that, let's describe the project. The person who originally wrote it against JRuby, and he wrote it against JRuby 1.3. At some point after JRuby 1.3, we ripped a bunch of stuff that he needed out of it and put it into its own library. And then, like all great open source projects, it went into decay. But one of the downsides is you could still use it today, but it would only support 1.8 syntax, which is a problem. And so Eric wanted to fix that. A second goal we had was that if there was any really interesting functionality that was in our sense that would be useful for the JRuby parser project itself, that he would go and move that in, or implement it differently, but move it in. So he did that, and it's good to go, except our sense hasn't been released. So we have to talk to Matsuyama-san and figure out how to get this released as a new gem. Eric added this really cool tree differencing support so that you can compare two different subtrees and do all sorts of things with it. And one thing that he did with it concretely is he made a gem called SmartDiff. So if you go and take a diff between two files, you'll get an HTML file that looks like this. You'll see the blue and gray highlighting back and forth. SmartDiff's actually able to tell that I just switched the order of these two files. And then you'll see that typical green and red output for things that are added or deleted. It's pretty cool. So you can use this, just gem install.
This is just built on top of RSense, so there's obviously a lot more stuff we could do with this.
Oh, this is actually just built on JRuby parser.
Oh, it's just built on built on a parser.
Yeah. JRuby Visualizer is by Maximilian Konzak. He's not here today. We need to have better tools to go and analyze stuff at the IR level. We have a lot of compiler passes running, and in particular, eventually we want to get this tool to the point where you can go and run your application and it'll generate an event stream. You can save that event stream, give it to us, and we can look at all the changes that are happening into IR and figure out what went wrong.
Right, see why it's not optimizing what it should be.
It's a GUI-based application. It's written on top of the JRubyFX gem, which is something that myself, Eric, and Max work along with, mostly ByteIT 101. I can't pronounce his last name, so I'm just going to use this handle. But that's an awesome GUI toolkit, JRubyFX. Use it. Okay, so here's just a couple of screenshots. If you go and click on the AST on the left, it'll just scroll to wherever on the right and show you what code that is. So there's a little bit of traceability introduced. At any point, I don't expect you to read that, but it's more IR output. Oh, actually, that's bigger than I thought. It'll actually ask for the compiler passes executed, and you can step through those and then pop up the IR view to see what's changed. We actually want this to be a more smart diff format to actually get better information how it's changed, but it's a Google Summer of Code project. The guy can only do so much. And lastly, you can go and look through it, the control flow graph, and we want to go and add more windows for more stuffs. Okay.
Another project we had this summer, Chamila worked on DTrace support for us. So Ruby 2.1 added DTrace probes. I think that was Aaron Patterson added that. We wanted to have the same thing, and Chamila came along and decided that that was the project he'd like to do for Google Summer of Code. It turns out OpenJDK does have DTrace support in it, so we could just build on top of those existing APIs. Now what we have right now, it's about 90% complete. And it passes a lot of MRI's tests for the functionality that we've implemented. But the thing we found out during the process is that unfortunately the DTrace support in OpenJDK only exists on Solaris right now. So we're looking at other options, pulling the DTrace support over to the BSDs like OS 10 where we have DTrace, pulling over the same APIs to Linux equivalents of DTrace, or possibly calling out to an external library. But we do have the code available. We're going to try and get it merged in at least for the Solaris platforms and then see what we can do for others. Shoes. Shoes 4 was another project that came on this summer. We've also did some work last summer, too. Tobias worked on this one. So Shoes is basically Why the Lucky Stiff's GUI environment. It's very clean, very simple to use. He wanted to come up with something that would be really trivial and fun to build complex GUI applications with. Shoes 4 actually made the decision last year sometime, I think, to move to a JRuby-only backend. There's a lot of reasons for this. Most of them, portability, not having to build the libraries over and over again, and having a consistent experience across all platforms. Building it on top of GTK or Win32 or whatever else never worked great across platforms. Things always felt a little bit different, and it was very difficult to ship applications since everybody needed to install all those extra libraries and build them for that platform. In the other room, in one of the salons, there's actually a talk on an application that uses DRB and Shoes 4 to do a space team-like pirate game. And that's Davey, Eric, and Ryan are talking about that in the other room. And since they couldn't be here and we couldn't be there, I thought we'd get a video from them to show this application running. And so this is written all in Ruby code using Shoes, which is backed by SWT, one of the JVM GUI libraries. Anybody play any space team players here? Not too many. The goal basically is you have 2 or 3 or 4 people, and it shouts out commands to you, and you have to do them quickly, or yell it out to your friends so that they'll do the commands. So there you go. So that's fun, and it's cool that it's actually being used now. Some more Google Summer of Code stuff we don't have time to cover. More work on Rubato, which is JRuby on Android, trying to strip down the runtime, improve performance, make it easier to build Android applications entirely in Ruby. Asakawa Ryu did that. Shoes 4 hackety hack support. Faraz did that. We mostly let the Shoes guys mentor that, so we didn't track that very much. For the second year in a row, we had 2 students working on Crypt. Crypt is a new encryption encoding library for Ruby intended to hopefully replace OpenSSL at some point, but implemented in Ruby where it can be, native where possible, and supporting all the implementations at the same time. So we've always got a good, solid encryption library. And we're very happy that we're able to support that every year in Google Summer of Code. We also had a student explore JRuby on embedded devices like Raspberry Pis and stuff like that. He basically came up with a bunch of different matrices of which libraries, which JRuby versions work on which platforms with which embedded JVMs. And we've got all that information available in the JRuby organization on GitHub. So, wrapping things up, emphasizing that JRuby is just Ruby. It just happens to be on the JVM. We're working with the MRI and the community a lot more and more in the future. If anybody has gems or libraries you're releasing, please turn on JRuby and Travis. If it's not passing, let us know and we'll help you figure out why. And if you're not trying JRuby right now, give it a shot. Let us know how it goes for you and let us know what we can improve. So thanks.